Welcome to the deep dive. Today we're opening a brand new window on the universe. We're going to be exploring the world of gravitational astronomy.
And we're doing that through the eyes of Nobel laureate Kip Thorne and the just monumental LIGO discovery.
Right, and this wasn't an overnight thing. We're talking about a project that took, what, half a century and something like 1,200 scientists to pull off?
It really did. And that first definitive observation, the one on September 14th, 2015, that GW150914 signal, it changed everything.
So let's start there. To really get why this is so huge, you have to understand how different these waves are from, well, from light, from everything we've ever used to look at the sky before.
Exactly. I mean, think about it. For all of human history, astronomy has been about catching electromagnetic waves, radio waves, visible light, X-rays. They're all just ripples in space-time.
They travel through space.
They travel through space. But gravitational waves are completely different. They are oscillations. They're vibrations of the fabric of space-time itself.
The actual shape of space is...
It's flexing, it's stretching, it's squeezing. And here's a really crucial part. Because they are part of space-time itself, they are almost never absorbed or scattered by matter.
So they just pass right through everything.
Everything. Stars, gas clouds, planets.
Yeah.
Which means they carry this, this incredibly pure, unfiltered message from cosmic events that are completely invisible to us otherwise.
Okay, so that's the why. Let's get to the how. The core idea came from Rainer Weiss back in 1972, right? This L-shaped laser detector.
That's right, an interferometer. But the concept was one thing. The engineering challenge was on a completely different level. It was almost science fiction.
And people knew it. I mean, Kip Thorne himself, one of the fathers of the project, was a massive skeptic at first.
Oh, absolutely. He was. The required precision was just staggering. They needed to measure a motion, a vibration, that was 1 trillion times smaller than the wavelength of the laser light they were using.
1 trillion times smaller.
It's a number that doesn't really mean anything. It's so small. Thorne even put a note in his famous 1973 textbook, Gravitation, basically calling the whole idea not promising.
So what changed his mind? What was the moment he went from skeptic to one of its biggest champions?
I think he just realized what the payoff could be. If they could pull it off, it wouldn't just be a new telescope. It would be a new sense. A completely new way to experience the universe.
And what a payoff it was. That first detection, GW15091 Pime, it was the merger of two black holes, a compact binary destruction.
And the signal itself, when it finally arrived after traveling for over 1 billion years, distorted the 4-kilometer-long arms of LIGO by a length of precisely 10 to the minus 21.
Okay, 10 to the minus 21. Put that into perspective for us. For you listening, what does that number actually mean?
It means measuring a change in the distance to the nearest star, that's Proxima Centauri, about 4 light years away, and detecting a shift in that distance equal to the width of a single human hair.
That is just impossible.
It feels like it should be.
So, okay, detecting it is one thing, but understanding it is another. When two black holes are whipping around each other at like half the speed of light, surely all our normal physics equations just break.
They do. The standard post-Newtonian approximations, they work fine when the black holes are far apart. But for that final violent collision, they're completely useless.
So you need something new.
You need a whole new field, really. It's called numerical relativity. This is where you enter the world of geometrodynamics.
Geometrodynamics. I love that word. It sounds like a force of nature.
It is. It's the study of the nonlinear dynamics of curved spacetime. You use supercomputers to run these incredibly complex simulations, like the SPECI code, to compute the exact shape of the gravitational wave during that final merger.
And those simulations, the visualizations that came out of them, are just breathtaking.
They really are. You can see it. About 60 milliseconds before they collide, the space around each black hole is depicted like this deep whirlpool just dipping down.
And then at the moment of impact.
At the moment of impact, the simulation shows a, quote, veritable storm in the shape of space-time. It's not an explosion in space. The storm is space. Space itself is writhing and churning like a violent ocean.
And then it's over.
In a fraction of a second, the storm subsides, and you're left with just one single, quiet, merged black hole.
It's amazing. But to even get a clean enough signal to verify those simulations, they had to deal with something way less glamorous than space-time storms.
Oh, yeah. They had to deal with noise. The sheer overwhelming noise of planet Earth.
And this is where it gets kind of ironic, doesn't it? You have these brilliant theorists, people who think about the fundamental nature of reality, and they have to become Well, they have to become glorified plumbers and engineers.
Exactly right. Their contributions were incredibly down to earth. Take scattered light noise, for example.
What's that?
It's is stray laser light that bounces off the inside of the vacuum tube walls and then recombines with the main laser beam, creating what looks like a gravitational wave signal.
A phantom.
So it's like an echo, but with light. A perfect analogy. And the solution was purely mechanical. They had theorists design these internal baffles lined with deep, randomly sized saw teeth.
To break up the reflection.
Precisely.
Yeah.
It breaks the coherence of the scattered light so it can't mimic a real signal. It's basically soundproofing for lasers.
That's brilliant. What about other strange noise sources?
Well, there was gravitational noise itself, not from space, but from us.
Yeah.
Here, the theorist had to calculate the gravitational pull of, well, of everything.
You mean like a truck driving by on a nearby road?
A truck, a person walking, anything with mass. They found that a human being had to be kept more than 10 meters away from one of the LIGO mirrors while it was operating.
Just the gravitational pull of a person's body was enough to throw it off.
It would create an unacceptable oscillating gravitational force.
Yes, that's incredible. But there was one noise source that was a total surprise, wasn't there? Something everyone had missed.
There was.
Hmm.
And it came from a theory student, year 11. Everyone was focused on thermal noise, the vibrations of atoms and the huge, heavy mirrors themselves.
That makes sense.
But Levin discovered that one of the most serious sources of thermal noise wasn't in the bulk mirror at all. It was in the microscopically thin coatings on the surface of the mirrors.
The coatings, something they just paint on.
Something they paint on. It was a component that had been almost completely overlooked, and it turned out to be a critical source of noise they had to overcome.
So they've conquered the noise, they've made the detection. This is the high-frequency window we're looking through now, but this is just the beginning, isn't it?
Oh, it's just the very first step. We're really looking at a future with 4 distinct gravitational windows. LIGO and Virgo are the high-frequency band.
Okay, what's next?
Next is the low-frequency band. For that, we need to go to space. That will be the LISA mission, which is targeted for launch around 2030. It will detect things like supermassive black hole mergers. Then you have the very low-frequency band, which we're already probing using pulsar timing arrays. This looks for waves with periods of years, maybe from the cosmic dance of supermassive black holes at the centers of galaxies.
Which leaves the last one, the ultra-low frequency band.
And that's the big one. That's the ultimate prize, really. For that, you look for patterns, polarization patterns, in the cosmic microwave background, the afterglow of the Big Bang.
Why is that the ultimate prize? What can it tell us that nothing else can?
Because gravitational waves are our only hope. Our only direct way of seeing the first 1 second of the universe's life.
Before light could even exist freely.
Before that, yes. We might be able to see the waves produced by, say, the phase transition that gave rise to the electromagnetic force. We could literally watch the laws of physics being born.
So for you listening, what's the big takeaway here? We've opened this new window.
And just like when Galileo first pointed a telescope at the sky, we know it's going to bring enormous surprises, things we can't even predict.
But there's a specific, tantalizing possibility, isn't there? A really profound one.
There is. The most provocative thought is this. What if the primordial gravitational waves we eventually detect? What if they don't match our current theoretical predictions?
What if they look different from what Einstein's theories say they should?
Exactly. That difference, that disagreement between observation and theory, that signal will be our map. It could provide the crucial guidance we need to finally discover the long-sought laws of quantum gravity.
So these waves aren't just telling us about the past, they could be writing the future of physics.
They absolutely could. That is the incredible promise of this new era.